Okay, so this is assignment 4, the live solutions for it. And let's start with question 1A here. Now, actually, before I even jump into that, the first version of the assignment I had posted actually had a plus right here in the equation, which was a mistake on my part. Some of you solved and submitted the assignment before I had made the fix. If you did that, I still marked it right, no matter what, as long as you got the correct method and there weren't any other mistakes at all, because that wasn't your fault. But anyway, apologies. The correct equation is this one here, and I will do the solution for this one. So I may have marked you correct where you got a different answer. If it was because you had a plus in your equation, that was why. So anyway, the relative refractive index. So here we have the refractive index and the equation we're looking for. And this is just going to be 1.5 over 1 equals just 1.5. So this is the relative refractive index. Here we just have a thin lens made of glass, and it's in air. So we're going from air to glass and from glass to air. So we just take the two different refractive indexes, divide them. That's what makes this a relative refractive index. I think most people got this. So moving on, part B. Find R1 using that equation above. Now, we aren't given a focal point, so I'm going to ignore the part where power is equal to 1 over the focal point, or the focal length, I should say. So I'm going to start by saying this is my equation here. Boom. I'm going to go ahead and sub some numbers in. We were told it was 2 diopters. Our relative refractive index that we just calculated. We are looking for R1. And we are told that R2 is equal to minus 100 centimeters, I believe. Yes, negative 100 centimeters. Now, I'm going to do a little bit of simplification before anything else. 2 equals 0.5. 1 over R1. Now I'm going to make this a plus because I'm subtracting a negative fraction. And this will be 1 over 1 because I'm converting this to meters. I'm going to go ahead and multiply everything by 2 to get rid of that 0.5. So I get 4 equals 1 over R1 plus 1 divided by 1 is just 1. So I get 1 over R1 is equal to 4 minus 1. Bring that back up over here. And I get 1 over R1 equals 3. Now if I just divide 3 by 1, I still get 3. Haven't just changed how it looks, haven't changed the value at all. I'm going to go ahead and flip both of these fractions. So I get R1 equals 1 over 3 meters. And that was my final answer, using the corrected equation. So that was it for number 1. A relatively short question for how much setup there was. Now, question number 2. I'm going to go ahead and do my solution on the second, or an extra page immediately afterwards here. But so for the first chunk, we have an optical system with 2 lenses. The first lens, lens A, is a negative lens. The second lens, lens B, is a positive lens. I tell you what the focal lengths are, and I tell you the distance between them. A few people missed this part. Lens B is located 10 centimeters behind lens A. That is important for later on in 2 spots. We have to consider that 2 or 3 times. 3 times it looks like. But 3 times. Part A, find the location of the final image produced by the optical system. Now, before I jump into this, I did give you the option of using a 2-scale ray diagram with minimal calculations alongside it, or calculate everything without the use of a diagram. Most people went ahead and just did all of the calculations, which is what I'm going to do. So let's get to it. 2A. Find the location of the final image produced by the optical system. So, 2A. I'm going to start with 1 over FA, 1 over DIA, plus 1 over DOA. This is just our thin lens equation, and I'm going to go ahead and plug some numbers in. So 1 over the focal length of A is negative 0.05 meters. We are looking for this image distance. We don't know what this is. I'm going to add 1 over the distance of the object to lens A. We were told that was 20 centimeters, so that's 0.2 meters. Now, the reason I'm looking for the image of A is because I know that the image created by the first lens is the object for the second lens. So first I have to figure out where this is before I can figure out where the final image is. So, solving for this, I'm going to have 1 over DIA is equal to negative 1 over 0.05 minus 1 over 0.2. And this will get me, let's say negative 4 over 0.2 minus 1 over 0.2, which will get me negative 5 over 0.2, which is also equal to negative 1 over 25, or no, sorry, I'm skipping ahead. Thinking too far ahead here. This is also equal to negative 25. Now, this is still 1 over DIA. So, to actually find DIA, I need to take the reciprocal, invert this basically. So I get 1 over, negative 1 over 25, or negative 4 centimeters. Now, I'm going to have to use this to find the image location from the second lens, lens B. I'm going to shrink this down a little bit. So, DIA, the image from lens A, is going to become the object for lens B. Now, I also know that lens A and lens B are separated by 10 centimeters. And I know that DIA is equal to negative 4 centimeters. And this means that DIA, the image created by lens A, is 4 centimeters left, because it's negative, of lens A. Therefore, the object DOB, our image that is now our new object, is a total of 4 plus 10, or 14 centimeters from lens B. So that was a very important step here. You do have to take into account the distance between the two lenses. So, because of this, I can say that DOB equals 14 centimeters. This is positive because it's an object on the left-hand side of the lens. It is an object on the left side of the lens. Again, that was a trickier part to this as well. And just shrinking that down to make it fit better. Okay. So now we can go ahead and start our calculation for the final image distance. So I get 1 over the focal length of B equals 1 over the final image distance for B plus 1 over the object distance for B. I'm told that B has a positive focal length of 7. So 1 over 0.07 equals 1 over DIB plus 1 over 0.14. Again, this is because of what we just calculated, the distance between. And it is positive because the object is on the left. The focal length is also positive because we're told it is. It is a positive lens. So, rearranging by subtracting 1 over 0.14 from both sides and writing DIB first, I get 1 over 0.07 minus 1 over 0.14, which is the same as 2 over 0.14 minus 1 over 0.14, which is just 1 over 0.14, which is equal to 1 over DIB. And I'm going to go ahead and flip both fractions here. So DIB is equal to 0.14, or, sorry, forgot to turn my phone off, or 14 centimeters. I would have accepted either. I'm going to write 14 centimeters because most of my other measurements are in centimeters right now. So our final image location is 14 centimeters. Now this is positive. That means it is 14 centimeters right of lens B, to the right. So for 2B now. To B, I ask you to find the optical power. I'll flip back here. Find the optical power of the system. Now, this one I was a little bit more lenient on because the equation I gave you was just P total equals PA plus PB, which is true, but this one's mostly for lenses that are in contact. If you just went ahead and used this and you got negative 5.7 diopters, I gave it to you because I was a little bit unclear in my instructions on how to solve a problem like this. So I gave it to you. That was fine. But I will go ahead and show the solution using a formula that I did not put on this sheet, but I absolutely should have. So this formula was using an equivalent focal length. So I know that power is equal to 1 over the focal length, but for two lenses that are not in contact, I have to use something we call an equivalent focal length. So that's what FEQ is going to stand for here. And it's going to look very similar to our thin lens equation. So we've got both focal lengths added together. And this is where it starts to look a little bit different. Minus d over f1 multiplied by f2. So going ahead and plugging in for f1, that was negative 5 centimeters, so negative 0.05 plus 1 over 0.07 for 7 centimeters minus, now d here is the distance between them, which was 10 centimeters, so 0.1 meters, and both of our focal lengths multiplied together here. So I had negative 0.05 times 0.07. And simplifying a little bit, I end up with negative 20 plus 100 over 7, plus these two negatives come together to cancel out, and we end up getting a positive. This is 200 over 7. And if you add all these together and put them as a decimal, I get 1 over the effective focal length, or an equivalent focal length, of 22.86. Now I'm going to go ahead and plug this straight into the power equation that I wrote just above. Now power is just equal to 1 over the focal length, which is why I left my answer here as 1 over the focal length. So if power equals 1 over F equivalent, it's just equal to 22.86. Diopters are our units here. So power equals 23 diopters, rounding to the nearest whole number right here. So that was 2B. I will box that off. 2C. This one asked us to find the total magnification of the optical system. So for total magnification, I'll call that MT. I get MA multiplied by MB. And magnification, we get a couple of different equations to use here. We can either use height or we can use distance. In this case, I have not told you anything about the height at all, so we can just use the distance instead. So, oh, actually, never mind. I did tell you it's 3 centimeters tall, so I guess you could go ahead and figure it out. But you would need the magnification first anyway, I believe. Either way, I'm going to go ahead and use distance. So, here I have MT equals negative DIA over DOA times negative DIB over DOB. Standard magnification equation here. So, our image distance from A was negative 4 centimeters. Over the 20 centimeter object distance. For DIB, the image I calculated was 14 centimeters away, and that was positive. Over, now the object, again, that was 14 centimeters away, positive. Now, the reason I did not bother converting to meters is because I have centimeters on top and on bottom of both of these, so the units cancel out. And I also just know that magnification has no units. So it doesn't really matter what your units are. As long as they are all the same, then you're good. Then they cancel out. So I left everything in centimeters because I just thought it was easier to deal with. So in this case, on the left-hand side, when it comes to simplifying, both these negatives also cancel out to become positive. So I get just 4 divided by 20, which is 0.2. And on the right-hand side, the 14s cancel out, and I just get negative 1. So my total magnification is negative 0.2. That was my total magnification. And lastly, I asked you for the salt characteristics of both images. Now, I didn't realize that my wording was poor on this question until I went to go start marking your stuff. I intended this to be done for both images individually, but it seems like some people read this and interpreted it as both images together. So start going from the original first object that's 20 centimeters in front of lens A to the final image. So some people interpreted this differently, and because of how I worded it, that's absolutely correct. So if you did it that way, I gave you the full marks, but some people did that way, still made mistakes. Some people did it the other way, still made mistakes. But if you did it that way, I may have given you full marks if you did that correct, just because this wording is a little ambiguous. It does leave room for that. I should have been more specific, so I wanted 2 separate salt characteristics. One of them for image A, one of them for image B. I wanted it separately, not together. So my wording here was a little off. But if it looks like you just did one for the whole system, I gave you the full marks, so long as it was correct. I'm going to go ahead and do it twice here. Once for image A, once for image B. So for lens A and lens B over here. So I'm going to do it twice. So I have my characteristics. Perfect. So, lens A, I know that the magnification for it was just 0.2. So this one is smaller. The attitude, that was positive, so this is upright. So that was a magnification of positive 0.2. So I know it's smaller, I know it's upright because it's positive. The location was 4 centimeters left of lens A, and the type is virtual. It's a negative lens, it's a diverging lens, so it creates an image on the same side as the object. It has to be virtual. So that is where that solution comes from. Now, if you calculated your magnification incorrectly and it was off, but you still wrote your salt correctly for that incorrect magnification, I still went ahead and gave you the full marks for it. But if you did still use a incorrect magnification, but your salt did not reflect that magnification that you calculated, I took a mark off. So as long as your salt characteristics matched the magnification that you calculated and the distances that you calculated, then I gave you the mark. Even if your distances and magnifications were calculated incorrectly, I still gave you the marks, even just for if it was the right method. So some of you may have been marked correct, even though your answer does not match what I'm doing here. That is why. But what I'm doing here is what you should have gotten. So for B, the magnification is actually just -1, which means it's the same size. Now, this is the same size as object B, which is image A. So if you did this for the whole system, the correct answer would be smaller. But again, I'm doing this separately. So same size, inverted because this is -1. This is 14 centimeters right of lens B. And this is a real image. This is a converging lens, a positive lens. They create real images it is on the opposite side of the lens as the object, the real light rays will converge to create a real image. Now, I believe that was it. That was everything. Yes, it was. So that was assignment 4. If you have any questions, please talk with me or email me. Up to you. Thank you for watching.